So this is environmental watershed surveys. I just told class that we're talking about kind of components, finishing up some components in watersheds. So that's what we're going to start off with. But we're ultimately looking at the watershed quality of water in those watersheds. So if I roll through this for you, again, just kind of, you don't need to take notes if you don't want to. If you guys are here and want to take pictures and stuff, feel free. But basically, why do we do watersheds, surveys of watersheds, is that small amounts of pollutants from large numbers of sources can basically add up. And so what you do here ends up in the Gulf of Mexico, right? Which you don't really always think about that, but like basically your car leaking out in the parking lot right now, leaking oil, goes into Lake Louisville. Obviously, nature has time to hopefully filter some of that out, but ultimately it leaves Lake Louisville, goes into the Trinity, then goes downstream, probably goes through a few more lakes before making its way ultimately to the Gulf of Mexico. So what you do here can add up and cause effects down the road. And then there's a lot of things that you do here that you don't even realize you're doing that ultimately affect the environment down the road. So studying all of those basically on a local level can help you start to do things to hopefully have a greater impact on a global level, if that makes sense. What are the benefits of doing these surveys? The government will actually do surveys of watersheds to some degree. Sometimes it's initiated by the public, but usually they do it to educate the community, to obviously identify problems, and then to, since you identify problems, fix those problems or help fix those problems, right? So that's pretty straightforward. So then the components that we didn't talk about with watershed stuff, we talked about like topography, stream order, what that says about streams, but then there's a few other things that we want to add in. One, we want to get the human element in there, and then two, there's a couple of things that just don't fit well with other things, so we just threw them in kind of at the end. So the first thing is latitude. If you look at your position north and south on the globe, that affects the amount of energy input in. We talked about that with seasons and days and months and years and all that kind of stuff. Earth's tilt basically makes less sunlight towards the poles, direct sunlight that is, which means less energy input towards the poles. Now what does that mean? That means that water doesn't convert to vapor phases as readily, so water stays in the watershed longer in those areas. We also talked about how energy input is what helps create weather and climate. So actually inputting more energy is what drives those weather events that then input water into the watershed as well. So latitude is one big component. Basically it determines how much energy is input, which then determines, wind, weather, and then evaporation rates, if that makes sense. There's this other thing that's called albedo. I don't know to what degree. I mean, surely I'll put it on the test or quiz, but basically albedo is just the reflectance of a surface. Okay, so the more reflective the surface is, the higher the albedo value, and that albedo value is kind of like percent of reflectance. So if you have a snowy area, white reflects a lot of light. White actually helps reflect the sunlight that's coming in, which then helps it not retain as much heat, so it actually keeps the environment cooler. If you have a blacktop, you've probably experienced walking on like a blacktop roadway in the summertime. It absorbs a lot of energy, which means it absorbs a lot of heat. It has a very low albedo value. So the more it absorbs, the hotter it gets, the lower the albedo value is. The less it absorbs, the less heat it takes in, the cooler it stays, the higher the albedo value. So if we have higher albedo values, that makes the climate cooler typically, because there's not as much energy being input into things to heat it up. So really, the cooler we stay, the better it is in terms of especially global warming. Obviously, temperature regime, so climate. is going to be a big one. I'm not going to talk too much about climate because we've talked about it before, but I do want you to understand that climate plays a big role in how water moves through watersheds. Obviously, if it rains a lot, you get a lot of water in a watershed. If you got dry climate, then you don't have a lot of water in your watershed, right? So we'll leave that at that and move on. Then climate also involves precipitation, temperature, relative humidity. We don't care, right? Why is it adding slides? That's interesting. So what I do want you to be aware of, though, is these graphs here, or these maps here. Notice that we are kind of on this dividing line on this one. This is the average annual precipitation. So we get somewhere between 50 to, well, we'll say 25 to 75 centimeters of rain, okay? So we're kind of right in this area. So we get 25 to 75 centimeters of rain. And then we get this much potential evapotranspiration, meaning we lose this much water. So we're in this 75 to 100 in losing. So we get 25 to 75, and then we lose 75 to 125 or whatever, or 100, right? So that means that we live in an area that is a deficit. So we are in the 25, or negative 25, sorry, well, basically the 0 to negative 50 deficit range, and that's in centimeters. So we're talking about, 50 centimeters of deficit in water every year. And that's why in any given year you see that we have times of drought, that type of stuff, because we are in an area that is typically in a deficit. So the reason that we have built Lake Ray Roberts, that we've built Lake Louisville, that we've built all of these lakes in our metroplex is because we have large populations in an area that shouldn't have the water to support those populations. So we build these lakes in order to give us the water that we need, because we are typically in a deficit. Does that make sense? And then what you do here affects those lakes, so we have to be a little bit careful sometimes what we're doing here, otherwise we end up not having drinking water, right? So that's kind of where we're headed. The geology is another one. We didn't talk about this one, but soil types, rock types, all of that is going to be at play as well. Here in North Texas, we typically have what's called clay loam soils, or sandy loam soils, which clay loam would be kind of like you dig up some ground from your yard and you can squeeze it and it kind of holds together a little bit, kind of like clay, but it will crumble apart, which is where the sandy part comes in. And then we have soil that's a little bit sandier than that won't actually hold together very well, but it does have some kind of stickiness to it, if that makes sense. And that kind of soil is really good for agricultural purposes, and really it's pretty good for water retention purposes. If you're really sandy, water's going to move through it too fast, and if you're really clayey, is that even a word? I don't know, but clayey, then it's not going to move through as well. So basically the type of soil and rock structure that you have will determine how quickly water penetrates through the soil and can ultimately leave your watershed, right? Here in North Texas, like I said, we have a pretty good soil that can retain some water for us, and that's why our lakes, when we build reservoirs, the water stays in them, because we actually have clay-based and rock-based soils that are good for holding on to water. If you were out in the middle of the desert, sometimes you don't have that ability, so you can't build reservoirs. So that's why some places in the desert don't even have civilization, because it's not really attainable. Next is that's just talking about soil permeability. We won't worry too much about that. Groundwater, soil moisture, we're not going to talk about either. That's not as important. This, I do want you to see, this kind of is going to relate to runoff, and runoff is going to be our primary carrier of pollution. So our soil actually can help limit runoff. If we have a soil that can soak up water, it can soak up a lot of that water and it doesn't run off, which carries pollutants downstream, right? So if we can get good soil that takes water in, it can actually carry the pollutants into the ground, which I know doesn't sound great, but that gives it time to break down naturally before moving downstream. So it actually helps. But this graph right here is basically just showing runoff, and this graph could change in any given scenario, but basically it's showing that before a rain event, the soil typically has more moisture in it the deeper you go, right? And then once you get a rain event, you have a lot of water that's on top of the soil, and then that slowly starts to infiltrate into the soil, so that 3 days later you have water that's moved about a foot down into the soil. So you're constantly replenishing water down deep into the soil with rain events, right? If your soil doesn't allow that, then this graph would be skewed to where the bulges would stay way over to the right and then quickly come back to this area here. That graph, I don't know if I'll show you exactly that one, but it's going to relate to some later. This is kind of important, and we're going to talk about this with some other river features that we didn't talk about before, but basically your river systems are actually even with the water table that's below ground, okay? So the reason a river typically has water in it is because the ground has cut away from the rest of the ground and you can see the water table. And that water is constantly flowing towards the ocean. So groundwater itself, when it penetrates into the ground, that helps filter it, but ultimately that groundwater is still running towards the Gulf of Mexico, if that makes sense, which a lot of people don't think about. So groundwater is moving. It just doesn't move as quickly because it's being inhibited by soil. And we'll talk more about that later. Topography we talked about before. We talked mostly about slope. Aspect, though, is another one that we probably want to just understand, that the direction a slope faces is its aspect. So if you have a mountain and it faces the sun, then that side of, a mountain's going to face the sun on one side and then all the other sides won't, right? So on the side that faces the sun, though, it will receive more direct sunlight, so that will be the drier side of the mountain. Then the other side that doesn't get as much sunlight will be the wetter side of the mountain and the cooler side of the mountain, right? So aspect becomes relatively important because it can tell you how dry or wet a particular side of a hill would be. And then we talked mostly about topography and hills and water flowing downhill, so I think we're good there. The last thing is going to be, I think it's the last thing, is land use and vegetation. So land use is where humans come in, right? And then vegetation is, there's natural vegetation, and then there's also man-induced vegetation. So that can kind of go across both. But basically, vegetation is going to do a lot of things for us that we don't think about it doing. The first is that it slows runoff, which also inhibits erosion, which cuts down on sediment being carried downstream. So that in itself is important. If you ever have your yard loses its grass, then typically you end up where you lose the soil too, because the grass isn't there to hold the soil in place. So vegetation actually helps keep the soil in place. It slows runoff. It allows more water to be absorbed into the soil. And then there it says it reduces soil compaction. That's because the roots break up the soil and aerate it to help I don't know what you call that, expand it, basically. I said it does soil erosion. The one that I think is funny is you don't think about it, but it reduces the impact of raindrops, right? If a raindrop hits bare soil, then it explodes soil away from wherever it hit, right? And I mean, it literally looks like an explosion. But when it hits a leaf, right, that leaf takes the impact, catches it, and then drops it gently to the ground, right? And so the soil stays in place better because of that, which is kind of weird. You don't really think about it. And then it also will help influence the timing of snow melt and runoff, especially at elevation. A lot of your vegetation will aid in how fast snow melt occurs, and that's typically in the mountains. When you start to get snow melt, most of the trees are evergreens. They have leaves on them. They provide shade, which helps the snow stay there longer, even though temperatures are above freezing point, if that makes sense. So it can actually inhibit how fast snow melts. And then it also influences water yield, which just means that it allows water to stay in watersheds longer because it's done all of those things there to limit runoff, if that makes sense. Then with that, there's just like 2 more slides that I need to get through on this, and that's kind of using the land use to see what happens when urban things come in. So in a natural environment here, you basically get 10% runoff, and these numbers are, you know, geniuses calculate this stuff and whatever, but they're not like set in stone. There's differences, but generally speaking, 10% of the water will run off in a rain event if you have just a natural environment. 25 will go into the soil, and then 25 will go all the way down into groundwater. So if you're doing some quick math, you're like 50, that's only 60% of the water from the rain. Where does the other go? That usually goes into trees and bushes and all of that stuff, right? Then if we start to build houses in the area, so this is like light urban development basically, you'll now get 20% runoff. So now you already up 10% of your runoff, and it goes bye-bye, and then you downgrade your water that gets into the soil, which it's not going down a lot, but it does go down a little bit. And notice that you're basically at like 62% somehow. So by adding houses, you've changed how much is going into building plants too, if that makes sense. Then if we go into the more houses, then we get more runoff. So notice that the runoff numbers just keep going up, and then if you get highly urbanized, you get a lot of runoff, and then very little stays in your watershed, right? So you will see things in areas that are urbanized, especially now. Like back in the 80s, it was like hey, burn it all, build up new stuff. Now you see cities that start to regulate things because they take these particular things in mind. And now if you're building a building, you have to reserve a certain amount of trees. You have to build like a water catchment system. If you notice anything in Denton that gets built now that's large, it has some sort of water catchment pond near it. You go out by Collins, it has that pond in front. That's for runoff from the parking lot that catches that runoff and keeps it in that area a little bit longer, so that it has time to do what would be in a natural situation. Does that make sense? So where we're headed with this information, oh, I forgot this. And then this is also runoff after rain events based on urban, agricultural, forest, and then just forest, which forest is going to be pristine forest land. Agriculture is where you have pristine natural environments, but you're mixing agricultural things with it. And then agricultural is like, I am just raising a bunch of cattle. And then urban is, obviously, we've got a bunch of cities. So notice that the runoff events from urban happen real quick in a storm. And then the more natural it gets, the less runoff you have, and the more the water stays in the area. So what that does for us, by knowing all of that stuff, it now sets up where we can understand how we screw stuff up, and then what the government is looking for to see if it's screwed up, and then what we can do, obviously, to not screw it up or fix it if it is screwed up. Does that make sense? So we are done with talking about what makes up a watershed. Now we want to talk about how we screw up watersheds. Yeah?